Hi everybody. In this video I will be showing how to work with the application for a magnetic circuit calculator dash simulator that I developed for my undergrad thesis in electronic engineering. First we will see that we have two tabs, the guide mode and the calculator mode. First we will see the guide mode. The guide mode has exactly the same layout and all the things that you will see in the calculator mode, but it has already a preloaded design that we can load or simulate in this case. So we'll see that it will be creating two different graphs. One that relates the length of the air gap, this section, the length between the two yellow blocks, and the magnetic flux density or B field that will be created in the center of the gap or workspace. And it will create up to 4 different lines or curves that we'll see here for different currents that we could apply. I'll explain later that thing on the calculator side of the things. Maybe the most important plot here will be the linear response or the response of the whole circuit in the workspace at the center, just to be clear. So we'll see that for a specific desired current that we specified here, we'll be finding that it will be plotting a range that will show the saturations and the linear response of the circuit. In this case, the circuit is getting a saturation in around 13 milliamps. Also, for help, and also like I'm showing here that I'm using this to explain how to interact or how to relate these variables or these values with the actual form of the circuit. This figure I will be using a lot to explain that. It's like a top view of how a C-shaped core or magnetic core should see using these variables. Aside from that, we are using the curves of the B field for solid materials. Specifically, these materials are from Back Magnetics, a German company that provided us some materials that were really useful. These are actual experimental values that were gathered or measured with a BSM here in Colombia. Now in the calculator section, we can start. First, we need to specify the coil characteristics of our circuit. In this case, the simulator is using the thick coils or a multi-layered solenoid, which has different kind of values or concepts that we will be using to find the magnetic field inside of or at the center of the solenoid. In this case, we are using an inner radius, an outer radius, and the length of the coil. I'll explain the rest of the things next. For the inner radius, we could see that the width of this blue block will be the inner radius of this coil. In this case, we will be using 10 millimeters. For the outer radius, we'll be using 25 millimeters. We have to be clear that this is radius instead of diameter, just to be clear. Next, we'll be changing the length of the coil to 24 millimeters. That will be the same length of this blue block, just to be clear. Next, for these calculations, we need to define which wire we'll be using. And for this case specifically, we'll be following the AWG or American Wire Gauge standard. For this specific example, we'll be using the AWG 24 that has a wire diameter of 0.5 millimeters. Then we'll see that we can find the current needed to create this field, or we can find the field applying a specific current in milliamps. In this case, we'll be using the same limit current that this specific wire has. We load the coil, we will find that we can create up to 19k amps per meter H as an H field with this coil specifically. This will only help to ground the idea to see if the proposed thick coil is working or not for our simulation. Next, we will work with the core characteristics, with the magnetic core. In this case, we can specify which core we'll be using. Will be iron, mu metal, back of flux, back of perm, or ultra black. In this case, we will be staying with iron for this example. Here it shows the core or relative permeability of this material. Aside from that, we need to specify the core width. It will be applied for both the blue section and the red section of this magnetic circuit, or this diagram. In this case, it will be this width and this width that you can see here. For this example, we'll be using 10 millimeter width. And for this example, we'll be using a 10 millimeter thickness. Aside from that, I may need to change this thing, because since the radius is 10, actually no, the radius should be 5, my mistake. So we just change these things here. And actually, let's change again this thing. Let's say only an outer radius of 10, and then we can apply, we can keep 25 here, and we'll leave the AWG to 24. We can load again and see that it almost halved the H field that we are creating now that I changed these variables. So now we'll continue defining the constants that will define the shape of the magnetic core that we are using right now. So we define the core width and the core thickness. So it will be like in a cross-sectional view, a square. So for the core length in the blue section, we'll be using 25 millimeters. And for the core length in the red section, this one, it will be 35 millimeters here. Then we need to specify the gap width. The gap width is related with the yellow blocks that we have here. So we want to define the width of this yellow block. In this case, we'll be using a width of 10 millimeters. So the three pieces composing the whole magnetic circuit will be all with 10 millimeters width. This will make the calculations easier if you want to do it by hand. For the core length, that is the length of this yellow block, is the length for one of the blocks, and it is all symmetric. So we'll be using 21 of length. My mistake, 22. Because these will add up. And then finally we will define the gap length. The gap length, we will use 1 millimeter in this case. That gap length is this space or length between the two yellow blocks. And you'll see how this changed, because I could explain that. For this case, we'll be using 100 milliamps in the simulation. So we will use as an input the desired current that we'll be using, and it will show us what is the magnetic flux density, or P field, in the workspace. So let's load our design. As we are seeing, the saturation of the field is not showing, but that's because the program just updated after we loaded the design, and now the saturation current of the magnetic circuit is 200 milliamps. So let's update this thing here to 300. Now we'll see this. We're finding that after the 200 milliamps, we are finding a saturation field, or our field is stopped changing inside of our workspace. To find this saturation field, what we are using, or what's happening, is that from this the PSM, it finds the position in which, or the field in which, the material or the magnetic core saturates. So then this code behind the whole simulator will be finding like the short circuit saturation current, and will establish that that's the maximum magnetic field or current that the magnetic core can handle. Then it will stop like growing the response. So we can see that it creates two plots, like with the same example of the guide mode. But in this case, we designed and placed our new design of magnetic circuit. In this first plot, we can see that we can create a really big magnetic field, let's say, of almost 430 milliteslas. So for that, in this specific case, is applying a 300 milliamps current, and this is with a real small gap field. We're saying about let's say 0.1 millimeters. But in this case, we want to see this because if we are designing our circuit and we know that we need a desired or a specific B field on our workspace, and we can maybe modify and get a smaller workspace, we can see a possible outcome of that idea. Aside from that, we can see now again the linear response or the response of the whole workspace, in which we can see the most important part, the linear response that we can find, and how it relates the source current that we are applying to the solenoid in our circuit, and how it's creating a magnetic field in the work area of our magnetic core. For this reason, in this case, we can see that for the 1 millimeter gap length, we will have around or a maximum of 90 milliteslas in the workspace. That could be better, that could be worse, but we can start modifying or doing a better design of our circuit to achieve better values. Aside from that, the circuit lets you know what will happen in a hypothetical case that you want to do or use a smaller gap, that we can see that it grows almost to the double or even more of the field. And what will happen if we increase the length of the air gap? So we'll see that that's a little bit different. Aside from that, I will say that knowing all of this, you should already be prepared to start using the simulator. Thank you very much.